we said that torque is just something that can produce an angular acceleration. And we defined what the lever arm was. We said that was the point from where the torque, from where the force was being applied to the pivot point of the object. I think we also talked about that force has to be applied perpendicular to the lever arm, because if you're trying to turn a wrench, it doesn't make sense if you're pulling parallel to the wrench. So I believe where we left off was with torque equation, or maybe we even got the torque equation down. Cool. So we will get into some sample problems real quickly with torque. So the equation for torque, and I'll put it up on the board, and this stuff will be pretty straightforward at the start, and then it'll get harder as what normally happens. But the equation is R. It says R perpendicular to F. I'm going to write that as R times F perpendicular. The reason why is we usually find the amount of force that's perpendicular to something. So the equation we got, I'll write it right here, is R times the force perpendicular. We already said the units for stuff, where a meters times Newton is the unit for torque. And just as kind of a general rule, since we can't say like to the right is positive, to the left is positive, we have to say that counterclockwise. That's not how you write counterclockwise. That was too many C's. Counterclockwise torques are positive, which makes clockwise torques as negative. If you forget which way counterclockwise and clockwise is, refer to the clock, which is now working again. But throughout this torque kind of intro stuff, and these will go really quickly, keep in mind that things rotate about a certain axis. So like if I picked up this broomstick, I could rotate this broomstick about the axis that's attached to my hand, or I could move the axis of rotation further inwards. So whenever we're doing torque stuff, think about what axis. So whenever I say the word torque, I'm going to want you to think like, which axis is this actually rotating about? But in this question, it says that there's something being applied to the end of a door, 5 newtons applied to the end of the door that has a width of 2 meters. So I'm going to draw out my lever arm, which is where the force is being applied, the distance from where the force is being applied to our axis of rotation. So our axis of rotation is right there. I usually put an X where the axis of rotation is, just to show that that's the axis of rotation. It's rotating about the door hinge. If this force is 5 newtons, the distance of our lever arm is 2 meters. Because that's kind of what's given in the question. Torque is R times the force that's perpendicular to the lever arm. The distance is 2 meters for our lever arm. The force that's perpendicular, is all that force perpendicular, or do we need to do anything with an angle? All that force is perpendicular. So that's a 5 Newton force perpendicular. So our amount of torque is 10, either meters times newtons or newtons times meters of torque. Thumbs up, thumbs down, thumbs sideways. Oh, cool. Rambling on, and we'll get through this as quickly as humanly possible. Next one, force is applied to the end of a door that has a width of 2 meters. The force is applied at an angle of 50 degrees to the surface. What is the magnitude of the torque about the axis of rotation? First thing, figure out where your axis of rotation is. Right there is where the thing is rotating about. Is all that force perpendicular to our axis of rotation? Nope. So we need to figure out how much of it is perpendicular to our axis of rotation. So we need to set up kind of a right triangle that'll allow us to figure out how much of that is perpendicular to the axis of rotation. If this angle is theta right there, then which other angle on the right triangle that I just drew is theta? 90 degrees. Like this one?
No, that one.
This one?
No.
This one?
Yeah.
So if this one's theta,
No, the other one.
this one?
No.
That one?
Yeah.
If that's a 90-degree angle, then those would be complementary.
It would be the one.
This guy? Yeah. So there's our angle theta. We know that the force is 5 newtons, but we need to figure out what this side of it is right there. The side of it that's actually perpendicular. What's up, Natalie?
You couldn't do it the other way and like draw a triangle straight out?
You could totally, like that,
Yeah, and then say theta was there.
you could totally do that if you wanted to.
Okay.
Yep.
Okay. That's it. Okay.
Yeah, either way is perfectly fine. The reason why I did it like this is because doing that might make me think that the force is being applied at a different spot.
Oh, I see.
But since the force is being applied at this spot, I wanted to kind of set that up. But if you want to do that to find the side and then transfer it over, that's perfectly fine. So either way, the side that we're trying to find, is that opposite or adjacent, sine or cosine?
Sine.
Sine, so that's 5 newtons times the sine of, is it 50 degrees? Sine of 50 degrees. That's how much force is perpendicular. So if we're trying to find the torque is the lever arm times the force perpendicular to the lever arm. The lever arm we know is 2 meters. Force perpendicular to the lever arm is 5 newtons times the sine of 50 degrees. I don't know what the answer is to that. 7.6 something? 6.6?
Yeah.
Newtons times meters? Cool.
Is
The
it
angle down where it was, I just don't know like it's saying that.
is it always gonna be sine?
No.
Because that's weird. 'Cause
Okay. Because what if it was
when we wrote down the equation.
what if it was defined as that angle?
Yeah, I know, but like when we wrote down the equation, it said TR perpendicular to F is equal to RF sine of theta.
Mm-hmm. It's not always sine though.
Why did they do that?
Turn the page.
Is that like what's in?
That's what's on the reference sheet.
That's stupid.
You just gotta know what's going on.
And then we just do that to show that there's some angle being there, so you see the sine or cosine.
Next one, force of 5 newtons applied to the middle of a door that has a width of 2 meters. If the force is applied directly perpendicular to the door, what's the magnitude of the torque about the axis of rotation? Step 1, figure out your axis of rotation. Step 2, still in the same spot. Step 2, figure out your lever arm.
1 meter.
R equals 1 meter. That's the distance from the axis of rotation to where the force is being applied. Is the force applied perpendicular? And we are good. Torque equals R times force perpendicular. The distance is 1 meter. The force applied is 5 newtons. The amount of torque there is equal to 5 newtons times meters. And for the last couple also, we kind of forgot to say whether it was positive or negative. So in this one, is this force trying to make that thing spin in a clockwise or a counterclockwise direction? Counterclockwise direction. Since counterclockwise torques are positive, this is positive 5 newtons times meters. Kind of move on to the next one. If it was trying to make it spin the other way, it would be a negative torque. The next one. Force of 5 newtons is applied on the hinge of a door that has a width of 2 meters. Force is applied directly perpendicular. What is the magnitude of the torque about the axis of rotation? Step 1, find your axis of rotation. Any distance is a force being applied from the axis of rotation? 0. So how much torque do we have? Torque equals 0 newtons times meters because the force is applied at the axis of rotation. Next one. Find the axis of rotation. Find the distance of our lever arm. What do we got for that lever arm distance?
1 meter.
R equals 1 meter. Force is being applied perpendicular, so we're good. Torque is equal to R times the force that's perpendicular to our lever arm. 1 meter. Our force is 5 newtons. But in this case, is that force, is the torque trying to make it move in a clockwise or counterclockwise direction? Clockwise direction. So our ultimate torque of 5 newtons times meters should be negative 5 newtons times meters. Final one, then we'll move on to some more difficult problems. Force is applied in the middle of a door that has a width of 2 meters. Force is applied at an angle of 50 degrees. We're trying to figure out how much force is perpendicular to the door, so you can kind of set your triangle up where that is the same as that. In order to find the perpendicular side, sine or cosine?
Sine.
Sine. Identify your axis of rotation. Identify the distance of your lever arm. What's the distance of the lever arm?
1 meter.
1 meter. Nice. We know that's 5 newtons. The angle's 50 degrees, so therefore this side, the perpendicular side, is 5 newtons times the sine of 50 degrees. When we find our torque, I'm not going to write out the equation. What do we get?
3.83.
3.83 newtons times meters, positive or negative?
Positive.
Positive, why?
If it's going from.
Trying to make it spin counterclockwise, so positive. Cool. If you are good, you can high five your person, you can take the torque thing, put it away, and we will ramble on. You go. Nice touch.
More to this torque stuff?
Oh yes, there's more to this torque business.
Torque is a real torque. It's really. Say it 10 times fast.
10 times fast. Newton's second law. Have we done Newton's second law yet? Do we remember to talk about Newton? Have we remember to talk about Newton's second law yet?
Yes.
What were balance forces?
No acceleration.
No acceleration. Balance forces implies constant velocity, or the thing moves at rest. It's either moving with constant velocity or remains at rest. Well, torque is just the rotational version of force. So what would balanced torques be then?
Object moves with constant angular velocity or remains at rest.
Balanced torques is when an object rotates with constant angular velocity or remains at rest. So balanced forces mean constant velocity. Balanced torques mean constant angular velocity. Object either rotates with constant angular velocity or remains at rest. If both of these things are happening at the same time, if you have both balanced forces and you have balanced torques, that means you've got something that is not changing its translational velocity or its angular velocity. When that happens, that's something called equilibrium. So the word equilibrium means when the forces are balanced and when the torques are balanced. So something that is not changing how fast it's rotating, as well as not changing how fast it's moving, is in equilibrium.
But if the forces are balanced, doesn't that mean the torques are? Oh no, it doesn't. Yes, it does, right? If the forces are balanced, then doesn't that automatically mean the torques will be balanced?
Is it possible for me to be walking this way at a constant speed? Is it possible for me to be walking this way at a constant velocity? That's spinning.
Yeah.
So then, does balanced forces imply balanced torques? Like, I can change how quickly I rotate
Yeah.
without changing how quickly I move.
Okay.
So one does not necessarily imply the other.
Are we gonna go over that? If you're moving and spinning at the same time.
A little bit. First of probably two, I just forget what time this class is. Is it 13?
You said 19.
19, nice, okay. First of two equilibrium sample problems. What we got here is it says two masses are supported at rest from strings around massless, frictionless pulleys. So these pulleys have absolutely no mass, they have absolutely no friction, but they have different radii. And I don't know if you guys can see, there's this little tiny pulley, and then there's that bigger pulley, and those things are attached to one another. So the little tiny pulley spins at the same time the bigger pulley spins, they're attached to each other. And there are two masses hanging off of each. First thing with an equilibrium problem or with a balanced torques problem, same thing as when we're doing balanced forces. Draw a free body diagram. But now that we're dealing with rigid objects, we're not just treating the object as a point and drawing all the forces on that point. We're drawing all the forces where they actually act. So for this basket of, what are those in there, potatoes? Potatoes. So for that first basket of potatoes, where does the force of gravity on the basket of potatoes act?
Straight down.
straight down. But where is it? Where is it acting? Yeah, it's at its center of mass. So the force of gravity on the basket of potatoes A is a force of gravity at A that's acting at its center of mass. What other forces are acting on A?
Force of tension.
Force of tension. Where is that acting? Right on the handle. So I'm going to start that right on the handle, and then should that be bigger, smaller, or the same if this whole system is at rest?
The same.
Same. Yeah. I'll call that force of tension of A. Let's go to our next bucket of, what are those, kiwi? Yeah. Our next bucket of kiwi. In our bucket of kiwi, what force or forces do we have acting on it, as well as where are those forces acting? FG downwards, and FT upwards from the handle. Balanced because the entire system is at rest. And I'm just naming the one on the left A and the one on the right B. What about the forces on that pulley system? On those two pulleys? Like,
Okay.
so like right here, FT is acting on the pulley?
No, from where it meets the pulley.
Like right there?
Yeah.
Okay. So there's FTA acting downwards. And how should that FTA compare to the other FTA?
At rest equal.
At rest equal. Those are Newton's third law pairs, just the same opposite directions.
Same thing for B, but it starts at the little.
Same thing for B, but it starts at the little pulley. So FTB at the little pulley. Now, anything else acting on our pulley system? There's got to be some force up, right? Or else this whole thing would just be accelerating downwards. No friction, but like, let's say this thing's like bolted into the wall. Or somebody's holding onto it or something's going on there. So there would be some force holding it upwards, right? So I'm going to put some force upwards. What do you want to call that? Force?
S for some.
Force of something? Sure. So force of something holding it up. Sounds good to me. So we drew a free body diagram for each object, and when we're doing it, we make sure that we start the force. We make sure that we start the force where it's actually acting on the object. So that first one, we're good. We've done that.
The FFS would be equal to
All of those together.
Yeah, F of S would be equal to the forces that are acting just on this thing.
Okay, so the FTA.
FTA and FTB. Yep. So next one, write the net force equation for each system. So we'll first talk about the system that's just this bucket. So the system is just that bucket, bucket A. You guys agree FTA equals FGA? Okay. What about the system that's the other bucket?
FTB is FTB.
Same thing but with B's?
Yeah.
FTB equals FGB. And then what about the system that's the pulleys?
FS equals FTA equals FTB.
Okay, so FS equals FTA plus FTB. Cool. So I'm going to call that P for pulley. Use that color. P for pulley. FS equals FTA plus FTB. Cool. Easy part is over. Let's ramp it up. Now we're talking about torque. Write the net torque equation for all forces external to the system. What system do you want to choose? What system would be rotating if anything's rotating? The pulleys would be rotating. That ain't going to rotate, that ain't going to rotate. Pulleys could rotate. So all forces external to the system of pulleys, just to kind of make sure that we know what we're talking about there. Now, whenever we're dealing with a torque type question, this should be something that's going on in your brain. It says about what axis. So write the net torque equation for all forces external to the system. What question should you be thinking?
What about what else?
Oh, great question, Natalie. What axis would that thing rotate about if it was to rotate?
The bolt.
The bolt. So our axis of rotation is going to be right at the bolt. Now, we have got balanced torques here, and what balanced forces meant was that the up forces equal the down forces, or the right forces equal the left forces. What balanced torques means is that the counterclockwise torques equals the clockwise torques. Or, in other words, the net torque equals 0. There's no net torque acting on this. The torques are just balanced.
Is that what he was like trying to explain in that one video?
Yes. Yep. Which of these forces, which of those three forces acting on the pulley are trying to make that thing rotate counterclockwise? FTB?
Does it say? Or are we just picking one? Oh, counter, yeah, no. I think it's FTA, because if FTA is pulling it, then it's going counter. And if this one's rotating this way.
Are you talking about the forces or the actual rope?
The forces that are being caused by the actual rope. So we got our bike wheel up here.
Okay.
FTB is like right here.
Yeah.
So if FTB was applied to it,
Yeah.
is that rotating clockwise or counterclockwise?
Clockwise.
Clockwise.
Oh, okay.
If FTA was applied to it, counterclockwise.
I thought because the forces are pointing up. The FT.
Oh, I see.
Which forces?
FTA, FTB.
Okay, but since we're talking about, since we're talking about the forces acting on this thing, we're talking about the ones that are actually touching.
But don't they have to be external?
Yeah, so they're external because it's the rope pulling on this, the same way that me pulling on the bike wheel is external to the bike wheel. So if our system's the pulleys, the ropes are external to the,
I guess I'm just confused because FTA and FTB
are inside those dotted lines.
They're not inside the system of the pulleys. They're within the system of the bulkheads, I guess.
So like this rope is inside the system of the pulleys? I'm not sure what you're saying.
I guess I understand now, but I just got confused.
Okay. Are you sure that if you don't understand, we can
No,
keep
I
talking?
got it. Just so the whole rope, not because I think I just got confused because we had two different forces for the rope.
Okay.
One that was attached to the pulley, and one that was attached to the rope.
Right. So the whole rope is not part of
So
the pulley.
it's just it's a rope to external.
Yes. Yeah. Nice. Good talk. What are we trying to? Oh, which one makes it go counterclockwise? So which one makes it go counterclockwise?
FTA.
FTA.
FTA. So our counterclockwise torque would be the torque from A.
Yeah.
Which ones would be clockwise torques?
The torque from B.
Okay. What about the force of something? Is that applying any torque?
Torque.
Yeah.
What's our equation for torque?
Force. Or
Lever arm times the force perpendicular to it.
yeah.
Is this force of something have any distance from have any lever arm?
Yeah. No.
It's being applied right at the axis of rotation, right?
So no.
Since this is being applied right at the axis of rotation, there's no torque being applied by that thing. Just like me picking this bike wheel up isn't going to make the bike wheel start spinning. So that since the force is being applied at the axis of rotation, there's no torque being applied by Fs. So I think that's it. That's all of our torques. So if we kind of keep writing that equation out, torque is R times force perpendicular. So torque A is R for A times the force perpendicular to that. So that's FTA. Is that force already perpendicular to our lever arm?
Yes.
Okay. So if we drew in our lever arm looks like that for FTA. And then it looks like that for FTB.
What does it look like for FTB?
Just the distance perpendicular to the force from the axis of rotation to where the force is being applied. Then the torque of B is the lever arm of B times FTB. Doing pretty okay so far. Any substitutions we can make? Like for FTA, is FTA equal to anything else?
Yeah, FGA.
FGA. And what's FGA equal to?
MG.
MAG. And we could do the same thing for FTB.
It's equal to MGB.
That's also equal to M times B times G. So we could rewrite this up here. I'm just going to erase where it says of pulleys and what axis. And that says RA times MAG equals RB times MBG. Do we know what RA is?
Yes.
Cool, we're given that. Do we know what MA is?
No.
That's what we're trying to find. Do we know what G is?
Yes.
Yep. Do we know RB is?
Yes.
Do we know MB?
Yes.
Do we know G? Cool. Go right ahead. Use one of those equations that we wrote in order to solve for the mass of basket A, which I think contains the potatoes, if I remember correctly. Make sure if it's 4.6 centimeters, make sure that you're putting that into meters before we do it, since the units for torque are newtons times meters. So if you have centimeters, got to convert to meters. I did this earlier on, and I get 0.56 kilograms.
I got 0.0.
I believe you. Definitely believe that could have been off by.
Did you get that too? I just redid it again.
Okay.
Wait, hold on, never mind.
Well, I mean, okay, we can reason through this to see if we're solid or not.
Yeah, it doesn't really make sense for the mass A bucket to be larger than that.
Why does it not make sense for the mass A bucket to be larger than the mass
Then
B
it would
bucket?
be lower than the other bucket.
Well, not necessarily that it would be lower than the heavier bucket, because if it's at rest, it could be at rest up here or it could be rest down there. But
Like,
if mass A was 0.56 kilograms,
Yeah.
then that would mean that there's a bigger mass a farther distance away than this mass is. So would it rotate if there was a bigger mass a farther distance away?
Yeah.
Yeah. So since we know that this bigger distance means that there will be a greater torque because of that bigger distance, what do we know has to be true about the force being applied up there? It's got to be a smaller force. So I agree with. Yeah, is it? I screwed up. 0.056 kilograms sounds good to me. Next part, determine the upward force of the pulley support. Any ideas? And any one of our 1,000 equations that has the upward force of the pulley support in it?
Isn't it Fs equals FT?
So Fs equals FTA plus FTB. Cool, sounds good to me. So Fs equals FTA plus FTB. And what did we say FTA and FTB was equal to?
FGJ.
FGA and FGB. So that's MAG plus MBG. Cool. So plugging that stuff in, I'm feeling confident about my answer to this one. I got 7.9 newtons.
Wait, question.
Yeah.
Are we on? Which one are we on?
Determine the upward force of the pulley support, which is what you called F sum.
I was confused.
I got 7.9, but I've been known to mess up. And especially if this was based off of the previous one, because we said that this was 0.056, right? So I could.
MAG plus MBG.
Yeah.
Mass of days.
So I think I might have messed that up because I was going along with the previous one that I got wrong. So let's try it out. 0.056 times plus 0.23 times 10. As did I. 2.86 newtons. I was, of course, just checking to make sure that you guys were paying attention was what went on there. It's definitely not that I screwed up the one before and then just carried it through. Final one. If the buckets were the same mass but pulley A was increased in radius, would the system begin rotating? Think about it for a second. Think about it for a minute or two. So if the buckets were the same mass as they currently are, but pulley A was increased in radius, would the system begin rotating? Think it out, and then we'll have some talk about it in about 2 minutes. If you guys want to talk together, that's fine, but I'm not going to say anything for a couple minutes.
Like if it's just a little, but it's still like, this is me fitting, no.
So you're at what?
I would say
Okay, no matter what.
because if this is just like line line, just put it to
Thoughts?
increase.
Well,
Oh, it would rotate.
it would rotate?
Yes.
What's your reasoning?
Because the force is applied to stay the same, both with the radius of A would increase. And
Okay.
It's a direct relationship between these two axes.
That was so on the right track to being an AP answer. Awesome. So we
I thought you
said
were gonna say but.
no.
On the track, but
So we said what? So we said
T equals R times F.
well, like what was your first thing? You said
The forces.
force is the same,
Are the same because the range.
FA is the same,
F is the same.
Mhm.
But the R increases.
RA increases.
And there's a direct relationship between RA
Okay.
and T.
So in this equation,
Yeah, T equals R times F.
okay.
And then I just drew the area.
Then you said since RA went up, TA went, torque of A went up. So why would that mean, now the one part that we missed, why would that mean that it would start rotating?
because if
Because of greater.
the forces would be unbalanced,
Yeah.
Forces would be unbalanced or torques would be
or
unbalanced?
torque would be unbalanced.
Therefore, torque A is bigger than torque B. So it rotates. Which way do you think it would rotate?
Down towards A,
Counterclockwise.
counterclockwise,
So
positive.
Rotates CCW. Nice.